Today's lesson is all about solving equations with complex numbers. The equality property for complex numbers basically says if we have two complex numbers and they're equal to each other, then the real parts are equal and the imaginary parts are equal. We've also seen that when you multiply conjugate pairs of complex numbers, we end up with a squared plus b squared solution, and this answer results in a positive real number. The fundamental theorem of algebra basically discusses how we can factor any polynomial into linear factors, and that every polynomial will have at least one solution and at most n solutions, whatever the power is on that polynomial. And then the last property is the reciprocal of any complex number is 1 over that complex number. Now the property of the sum and product of roots, we'll see that property, these properties in an example, how we can use these rules to write polynomials based on this knowledge. But first we're going to jump into finding pure imaginary solutions using the square root method we talked about in our last lesson. So let's say we want to solve 5x squared plus 20 equals 0 using the square root method instead of factoring. The first thing we would do is isolate the 5x squared term and the negative 20 and then divide by 5 so that we have x squared on the left and negative 4 on the right. Next, we can take the square root of the left and the plus and minus square root of the right, which will give us x is equal to positive or negative 2i. So we have gotten pure imaginary solution in this case. In example 2, the same thing holds true. It's just another example that you can do by yourself, or we can do together. X squared is negative 15. When we take the square root of x squared and both positive and negative square root of negative 15, the only thing that can be simplified is bringing out the square root of negative 1. By definition, that's I, and again, we have a pure imaginary solution. In example 3, we're going to use that equality property for complex numbers. So if two complex numbers are equal to each other, then the real part is equal to the real part. So the real part is negative 6 to replace x. And the imaginary part, 5yi, is equal to the other imaginary part. Dividing by 5i, we get y is 20i divided by 5i, so y is 4. For part B, we know the real part, negative 16, is equal to the real part in the second number, so x becomes negative 2, and the imaginary part, 3i, is equal to yi. Dividing by I, y is equal to negative 3. And finally, on part C, it's a little more complicated. We need to distribute and then collect like terms. But first I noticed that I could get the x terms on one side of the equation. So if we keep 2ix and then add the 1 minus I times x to the left side, and then leave the 3i on the right and add the 5i and subtract 3, we can collect like terms this way. So 2ix plus x minus ix equals 8i minus 3. And here we have 2ix minus ix, that gives us ix plus x. So we could factor out the x and have I plus 1, or 1 plus I, and 8i equals 8i minus 3. So solving for x, we can divide 8i minus 3 by 1 plus I to eliminate that term. And at this point with this fraction, our next step would be to rationalize the denominator by using the conjugate pair 1 minus I. So I'm going to come up here. X is 8I minus 8I squared minus 3 plus 3I, and then divided by 1 minus I squared. So X is 8 and 3, that's 11I, and this is going to become plus 8 minus 3, so that's 5, and then 1, this is going to become negative 1, so we've got plus 1, and that's going to be 2, so that our final answer in appropriate form is 5 over 2 for the real part, plus 11 over 2I for the imaginary part. So using that property of equality for complex numbers in that example. For example 4 and 5, we'll use quadratic formula to solve for complex solutions. So A is 3, B is negative 1, and C is positive 2, and X is the opposite of B, plus or minus the square root of B squared minus 4 times A times C, all of that divided by 2 times A. So our X coordinate is 1 minus 24, so that's going to be negative 23 divided by 6. X is 1 plus or minus the square root of negative 23 divided by 6. So we can take out the square root of negative 1 by definition, that's I, square roots of 23 over 6. Now in the last lesson we left our answer this way, but you can separate that to look like the appropriate format for complex numbers, with the real part being X equals 1/6 plus the square root of 23 over 6I, and then the second solution is X equals 1/6 minus the square root of 23 over 6I. So this is in proper form for a complex number, standard form. In example 5, same thing. We can't find factors of 5 that add up to negative 4, so it can't be factored over the real numbers, but we can use quadratic formula, where X is the opposite of B, plus or minus the square root of B squared, minus 4 times A, which is 1, times C, which is 5, all divided by 2 times 1. Simplifying that is 4 plus or minus the square root of 16 minus 20. That becomes negative 4 over 2. And then simplifying further, we know the square root of negative 4 is 2I. And breaking that apart, we have X is 4 divided by 2 plus 2 divided by 2. So we have 2 plus I. And we also have 2 minus I. So 2 solutions in the complex numbers. In example 6, this is an example of the multiplicative inverse for a complex number. So if we want to find the reciprocal of 3 plus 2i, that would be 1 over 3 plus 2i. And it's a division problem, so we want to rationalize the denominator by multiplying the fraction by 3 minus 2i, so we need a well-chosen 1 in that format. Then multiplying the numerator together, that's 3 minus 2i, and the denominator by the property of conjugate pairs, we're going to get a squared, which is 9, and b squared, which is plus 4. So we have 3 minus 2i divided by 13. And then separating that in proper format, we have 3 over 13 minus 2 over 13i to give us standard form for a complex number. This is the reciprocal of 3 plus 2i. Example 7 is going to go back and use that property to find the sum and the product of the roots of the equation. In order to do that, we need to find the roots to begin with. So using quadratic formula, x is 3, which is the opposite of b, plus or minus the square root of b squared, that's 9, minus 4 times 1 times 4, so that's 9 minus 16, all divided by 2 times a, so we got 2. The simplified form becomes 3 plus or minus the square root of negative 7. So if we take the I out and leave the square root of 7 on the inside, we have our roots. Now the property says that the sum of the roots should be the opposite of b over a. b is negative 3 and a is 1. So the sum of our roots should be negative 3, or the opposite of negative 3, which is 3. So let's give that a try to verify we do get positive 3. So the sum of our roots is 3 over 2 plus square root of 7 over 2i, and we want to add that to the other root, 3 over 2 minus the square root of 7 over 2i. And adding those up, the positive I and the negative I eliminate, and 3 over 2 is 6 halves, and 6 halves is 3, and 3 is the opposite of b over a. Since b is negative 3 and a is 1, the opposite of b over a is positive 3. That checks out. Now let's try the next property. That property said the product of the roots should be c over a. So we want to verify that. Is the product of our roots c over a? So that's what we're checking out. And the product would be 3 over 2 plus square root of 7 over 2i times 3 over 2 minus square root of 7 over 2i. Now, using that property of conjugates, we know that we're going to get a squared plus b squared. So a is 3 over 2 and 3 over 2. That's 9 over 4. And b squared is square root of 7 times square root of 7, and 2 times 2, that's 4. And 9 plus 7 is 16 over 4. And 16 over 4 is 3. So we want to go back and look at our equation. What is c and what is a? Well, c is 4 and a is 1. So yes, the product of our roots is the value in the equation. So this is just a way that you can check your solutions to make sure that you've done all of your work correctly with the quadratic formula in this case. And then here in our last example, we're going to use the property in a different way. This time we want to use that property to actually write a quadratic equation for the roots that they're giving us, and we're going to assume the a value is 1. So assuming a is 1, if a is 1, then we want to find out that the opposite of b over a is what number? So the opposite of b over a is got to be 0. Because we've got negative 5i plus 5i. Because these are our roots. Negative 5i plus 5i is the sum of the roots, and that adds up to 0. So figuring that out, if a is 1, then b is 0. And then the product of the roots has to be c over a. So c over a is the product of the roots, and negative 5i times 5i is going to give us negative 25i squared. And negative 25i squared is going to be positive 25. And if a is 1, then c is 25. So now we know c is 25. And using these three pieces of information, then we know we can write the equation y equals ax squared plus bx plus c, and that would give us standard form. So x squared plus 25 is going to produce the roots 5i and negative 5i. Now part B, it's a little trickier, so we want to add the sum 2 plus I added to 2 minus I is going to give us 4, and that has to be the opposite of B over A, and we were told to assume A is 1, which means B is negative 4. So this is the sum of the roots to get opposite B over A. And the product of the roots, 2 plus I times 2 minus I, is going to give us C over A, which is 4 plus I squared, that's 1. So 4 over 1 is 5, and C happens to be 5 since A is 1. Therefore, we know our equation based on the A, B, and C values. Y is 1x squared minus 4x plus 5. And that's the end of Lesson 9 in Unit 4.